तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome. In this session today we shall be starting with a new topic, namely that of recovery, that is how do we recover data, or how do we bring back a database into what we call as a consistent state in the face of any kinds of failures. Failures could be of different kinds, let us say disk crashes or power shutdowns or network connection failures or many different kinds of failures, and we are going to be somewhat specific when we say recovery. I mean, obviously we cannot recover data that were involved or that were being processed in main memory during RAM, I mean main memory during the crash, but and we can only recover whatever has been written onto persistent storage like disk. But is whatever that is written onto disk a good recovery, or should we is there some more semantics associated to what is written onto disk, and do we have to do something more when in order to recover from a crashed schedule? In order to answer this question, we need to know the concept of a transaction in a database processing environment. Therefore, the title of this session is called Introduction to Transaction Recovery. In fact, we are going to define the notion of correct recovery from a wrong recovery based on the concept of transactions. We are not going to be studying about transactions in detail here. They are covered in a separate topic under itself, because transaction and transaction processing itself is a vast topic with several different aspects to it, and we shall be concerned mainly with only the recovery aspect here when it comes to and we are using the term transactions to help us guide in deciding which kind of recovery is a correct recovery and which is an incorrect recovery. Let us first define the term OLTP. I am sure you might have heard of the term OLTP in several different contexts. It stands for Online Transaction Processing Environments. An environment that is a database system plus an application program plus any other associated accessories like networks and so on, that goes into form an environment that is meant for online transaction processing. What is meant by online transaction processing? As the name suggests, it is a processing environment that can interactively process database transactions. We will define these terms in much more in a much more accurate fashion later on, but let us first have a look at some environments that can be classified as online transaction processing environments. Some examples are like airline or railway reservation systems. What are the characteristics of such systems? One of the main characteristics that you can straight away see in railway reservation system, for example, is that there are several number of users who are accessing the database system simultaneously. That is, you might have experienced it if you have tried booking a railway ticket over the internet. Suppose a train is getting to be almost full, and if you delay in booking your ticket even by, let us say, sometimes even by a few minutes, then you might not get a confirmed ticket at all, and it might go into a waiting list. So that means at that particular instant of time when you were checking the status of tickets, there were several other people accessing the same database throughout the country. That is, they could be accessing via the internet, they could be accessing it via the via, let us say, some kind of queuing system that is across the booths or whatever, but whatever form, they are all accessing the same database, and several different transactions, so to say, are happening at the same time. And similar examples are that of banking systems, and especially in how cash is dispensed in ATMs or wire transfer mechanisms and so on. And other OLTP environments include supermarket checkout systems, and where customers come in with their baggage of whatever things that they have bought, and they have to be checked out and priced and billed and so on. And there are hotel and hospital systems, and trading and brokerage systems where buying and selling of shares keep happening continuously whenever trading is on, and several such sessions are happening simultaneously. Now let us take a scenario which helps us understand what should be the properties of these transactions or that go on in OLTP environments. Now consider a small banking example where different accounts are maintained in a bank. They could be on different databases or within the same database, or different locations or the same location, it does not matter. Let us just consider that there are different accounts, and this database is being accessed simultaneously by several users performing several transactions. Let us say one person is using net banking to transfer some money from his account to somebody else's account. At the same time, some other person is using an ATM to withdraw some money or deposit some check, or some check is getting encashed and some DD is getting encashed or withdrawn or whatever. Several things are happening simultaneously in the bank. Okay. Now among this, let us consider a small one particular example, that account number 2565 sends 2500 rupees to another account number 165. Okay. So let us say at time t equal to 0, however we define our time, okay, a transaction begins, or a set of database operations begins. The application program that is making this wire transfer will initiate some database operations which will first read the balance of account 2565. Okay. Now it will read the balance amount, and because it is a withdrawal from this account, 2500 will be deducted from this balance. And let us say we are using concurrent applications which can have different threads of executions which can run at the same time. So when this balance is being deducted here, at the same time the balance of the second account is being read, okay, of account number 165. And due to some reason this gets this thread or process gets swapped off into a disk by the operating system, and some other process is running, because note that operating systems have their own way of scheduling processes, and maybe some other process could be running at that time, and by the time this process comes back, it is time number 4, time t equal to 4. At this time a balance amount of 2500 is added to this account. Okay. Now meanwhile, let us say there is another transaction. Let us say the account holder of this account number 165 is meanwhile standing in an ATM and depositing certain cash, certain amount of cash into the ATM, or maybe he has sent a check and that check is getting cleared. Okay. So while this the person with account 2565 is performing this wire transfer, the person having account 165 is also depositing an amount of 3000 rupees. and it so happens that the way processes are scheduled, this set of operations, that is reading the balance of this account number 165 here and adding 3000 rupees is done before the previous transaction finished. That is before the balance of before an amount of 2500 was deducted from the that was based on the previous transaction. You can see what happens, what has happened now. The previous transaction has read the old balance amount and added, actually this should be added, I am sorry, there is a small bug here, this should be plus equal to, that is it has taken the previous balance amount and added 2500 rupees here, while before it could do that, the previous balance was read and 3000 rupees was added by the customer who is depositing his check from the ATM. Now what has happened here is that this entire transaction is lost, this entire series of operations is lost after time t equal to 4, because suppose this person had 50,000 rupees in his account, it will now be 52,500 rupees rather than 55,500 rupees, 3,000 plus 2,500 rupees. Okay, so 3,000 rupees is just gone, is just lost. Now as you can see, this is not an unrealistic situation, especially we just saw how today when we have facilities like net banking or ATM or booking train tickets over the web or using telephone calls or using SMS from mobiles and so on, this is not an unrealistic situation at all, because concurrency is concurrent activities are happening at the same time. I mean concurrent activities are happening all the while, and if you are not careful, such kinds of activities can result in an inconsistent database. That is, the entire transaction of depositing 3000 rupees is lost in this example. So what is the we said that if you are not careful, what is that care that you have to take, or what is that we need to remember when we are dealing with situations like this. The thing that we need to remember here is that the first two activities, let us say the first activity of a wire transfer between account 2565 and 165 is a completely different or is a conceptually separate or distinct activity from the second activity of depositing 3000 rupees. Okay, so the first activity is a conceptually or logically separate activity or functionality than the second activity. Such kinds of logical units of work are called transactions, and transactions activities in a transaction, that is the actual database activities in a transaction, should be scheduled in such a way such that these kinds of anomalies does not occur. Okay, so let us try to formalize these things in a little bit in much more detail. Now what is a transaction? A transaction is a logical unit of program execution. As we saw, the entire activity of withdrawing money from A's account and depositing that money into the B's account constitutes one logical unit of operation, and it is a combination of database updates which have to be performed together. They cannot be independent of one another. The withdrawal from A's account is not independent of the deposit from into B's account, and vice versa. There are several different definitions of transactions depending on where and how it's being used. Let us have a brief look at the different definitions of transactions, which makes it clear what are the different facets to handling transactions or recovering from transactions and so on. Firstly, we can define a transaction as a logical unit of work that is meaningful in the user's environment. As we can see here, the wire transfer, that is withdrawal of money from A's account, and depositing into B's account is a meaningful semantic activity as part of the user's environment, because that constitutes a semantic process in the user's environment, a wire transfer. Similarly, depositing 3000 rupees. In order to deposit 3000 rupees, there were two database operations that were done, that is reading the previous balance and updating the balance. So both these activities, that reading and updation, is one semantic activity, that is constitutes one meaningful activity, namely that of depositing a certain amount of money into a account. One can even define transaction as a logical unit of work with respect to concurrency control and recovery, and not necessarily in semantic activity in terms of the user's environment. In many cases, users, depending on at what granularity that you are looking at, users may not be concerned with what are considered transactions at the database level, but however we might have to club, or we might have to combine certain database activities into transactions in order to maintain consistency in the face of concurrency control and recovery processes. Transactions are also called atomic unit of work. Instead of calling it as logical unit of work, a much more stringent definition is to say that it is an atomic unit of work with respect to concurrency control and recovery. Atomic unit of work is a more stringent requirement than saying just logical unit of work. An atomic unit of work basically means that it cannot be subdivided into smaller works, that is either all of the activities of a transaction are performed or none of them are performed. You cannot perform half a transaction and leave it at that, or you cannot perform 90% of a transaction and leave it at that. Either you have to perform the entire set of activities of a transaction or nothing at all. And another definition that is generally used is that transaction is an atomic unit of work that when applied to a consistent database returns another consistent database, that is it is an atomic unit of work that is meaningful, that could be meaningful, that is it's the atomic unit of work with respect to concurrency control and recovery. However, not all atomic units of work that can be managed for concurrency and recovery could be transactions, because some of them could take the database to an inconsistent state. So transactions are sometimes defined as only those units of work that make transitions between valid states of the database. Now, what are the properties that a transaction should satisfy? That is, we have seen, we have motivated the need for transactions from several different angles. We first saw an example application where an example OLTP application where transaction processing or incorrect transaction processing can lead to anomalies, and we also saw different kinds of definitions that look at the notion of transactions from different levels. Now, how can we consolidate them together and synthesize what are the basic properties that a transaction should hold? Okay, so the basic properties that a transaction should hold are what are called as the ACID properties of a transaction. ACID that is ACID stands for atomicity, consistency, isolation, and durability. That is shown in the slide here. What is atomicity in the ACID property? Atomicity, we just saw in the previous slide that a transaction should be viewed as an indivisible unit of work. That means either all activities in a transaction should be performed or none of them. We cannot perform half a transaction and leave it. Okay. Consistency of a transaction basically means that if the database is consistent before a transaction, it should be consistent after a transaction as well. The transaction, the atomic unit of work, should not lead the database into an inconsistent state. What do we mean an inconsistent state? Any state that violates integrity constraints of the database. We saw how to specify integrity constraints and how they are enforced in the database system. The third property of transactions is isolation. we saw an example of transactions violating isolation in our banking example that we saw before. Isolation essentially means that even though activities in the database are happening concurrently, that is the readings and updates and reads and writes operations, whatever is happening onto the at the database level are all happening in a simultaneous fashion, the net effect in an OLTP environment, the net effect should be as though the transactions have been executed in some serial order. It does not really matter what should be the serial order, as long as we can establish an equivalence between the way in which database activities are performed to a serial sequence of executions. That is, it should be as though that transaction A was completed before transaction B began, and B was completed before transaction C began, and so on. And the last property of a transaction is called durability. That is, once a transaction finishes, or rather we use the term commit here, that is, once a transaction says now I have done all my work and you can commit whatever changes I have made into the database, once it is committed the changes are persistent, that is, you cannot roll back or you cannot undo the changes that are being made by a transaction after it has been committed to the database. That is, commit is something like, in order to understand the notion of commit, it is something like a physical activity. For example, dispensing money from an ATM is a commit operation. Once it is committed, once money is dispensed, you cannot roll back, you cannot expect the user to say no, we did something wrong, you have to put back the money that we gave you because some other transaction is conflicting with it. So once a commit operation is performed, it is durable, that is, the transaction cannot be rolled back, and we have to do something else in order to undo the operations of a transaction. Once you dispense money from an ATM, you have to do something else, you have to chase the person who withdrew the money and get back from him if required, and so on. Okay. So we cannot undo the transactions within the purview of the database itself. Let us look at examples where examples that specify each of these ACID properties of a transaction. Have a look at the slide here. Let us say the transaction involves again a wire transfer from account A to account B. That is, the transaction should be like this, that is, account A dot balance minus equal to amount, whatever amount has to be transferred, and account B dot balance plus equal to amount. Let us suppose that the balance, that is amount number of rupees has been debited from A's account, okay, and for some reason the database crashes. Let us say there is a disk crash or a network failure or whatever, or operating system crash or whatever. Now once the system is brought up again, that is, once there is a recovery process, this transaction has not completed. Therefore, in order to make it atomic, we have to roll back, that is, roll back the changes that we have made since the beginning of the transaction. That is, we have to put back this amount back into A's account and then restart the transaction once again. Otherwise, this will not be an atomic operation. This would amount to, if we did not perform this recovery operation, this would amount to performing half a transaction, and we saw that half a transaction is not an atomic transaction. What about consistency? Have a look at the example here again. Okay, this is again the wire transfer example from account A to account B. That is, the same series of operations have to be performed. That is, A dot balance minus equal to amount and B dot balance plus equal to amount. Now let us say that the query that has to perform these two things has been that is, the query plan has been performed, and these two operations are given to two different threads in the operating system, and it so happens that the thread performing the changes on B's balance is scheduled first before that of A. Okay. So let us say first B's balance, that is, B's amount is credited, that is let us say A is sending 2500 rupees to B. So we know the amount, that is 2500, so B's balance is added by a value of 2500, and however when trying to remove 2500 rupees from A's account, we see that A has 0 balance in his amount, he cannot make this payment. Okay, so this transaction fails, we cannot make this transaction. So in order to keep this transaction consistent, we have to deduct whatever credit we made into the account of B in order to bring back the consistency in the database system. Note that here there is no crash or anything of that sort, here there is a normative failure, the normative or failure with respect to norms, or failure which violated an integrity constraint. We can think of an integrity constraint that says that overdrafts are not allowed, that is the balance amount in a user's account may never be negative. So when we try to do this operation, that is when we try to debit 2500 rupees from A's account, we found that the balance has become negative and it violated the integrity constraint, which in turn caused the transaction to roll back, that is in order to maintain overall consistency in the database system. The third property is that of isolation. And isolation, like we said before, deals with concurrency, that is how do we handle concurrent operations being performed from 2 or more transactions simultaneously. So again consider the case of wire transfer, that is account A is transferring some amount to account B, at the same time the person holding account A is also withdrawing some money, that is the person holding account A had given a check at some time which is getting processed now, and at the same time the account holder is also withdrawing some money. Okay, so let us say transaction T1 is reading accounts A's balance, debiting the amount and crediting the amount to account B. Now let us say that A's balance will become 0 after debiting this amount, let us say 2500 rupees. Okay, and let us say the same amount is being also withdrawn by or being asked by this account holder for withdrawal. Okay, the net effect of running these 2 transactions should not be the case that both of them read the database or read the balance and see, okay, there is 2500 rupees, and then go ahead independently debiting them, debiting the account, because that would be incorrect, because we would have debited more than 2500 rupees from these 2 transactions, whereas that would not be reflected. So the net effect should be either T1 precedes T2, that is T2 begins operation only after T1 has completed, that is in effect that should be the case, in which case T2 will fail, or T1 began operations after T2 completed. It does not matter which is the serializable schedule, which is the serialized schedule that we want, is it T2 after T1 or T1 after T2. So in either case one of the 2 transactions will fail, that is either the withdrawal will fail or the wire transfer will fail. And durability, like we said, is a commit operation, that is once something is committed then it is not changed, and we gave an example of let us say money dispensing from an ATM. So once a commit operation is performed, it is safe to dispense money from the ATM, and we cannot roll back the transaction once the commit is performed. What are the different states in which a transaction is in, and this is important to know when we are trying to recover from a failure of a transaction. Now transaction is said to be in several different states depending on what has happened since it began. It is said to be in an active state, which is the initial state when the transaction is executing. When the last statement has finished execution and it is ready to commit, the transaction is said to be partially committed. When the transaction discovers that it can no longer proceed with normal execution because something else has happened, some crash or some violation of an integrity constraint or some violation of an isolation requirement or so on, when it has discovered something like that has happened, then it is said to be in a failed state. And once the transaction is rolled back, it is said to be aborted. And if the transaction successfully completes operation, that is if the ATM, let us say, successfully dispenses money, it is said to be committed, and either committed or rolled back or aborted state is called a terminated state. So this slide schematically depicts the different states in a transaction, and also shows from which state you can go to which other state. That is, from the active state you can go to either a partially committed state or a failed state, and you can also reach failed state from a partially committed state, that is after performing a few operations. And from a partially committed state you can if everything is okay, then you can go to committed state, or if things are not okay, you come to failed state, which in turn takes you to aborted state. Let us have a simple look at how these acid properties can be maintained, or what it takes to maintain these acid properties, and we are going to look at this simple example called simple technique called shadow copy. Shadow copy is extremely simple and extremely inefficient, and it is not used in practice. Several more sophisticated techniques for handling or maintaining acid properties are taken up in much more detail when we take up the topic of transaction processing itself. Here this is just to illustrate the concept of what it takes to perform or to maintain certain properties of a transaction. Now shadow copy transaction assumes the database to be a single file, and assumes that there is only one transaction that is active at any time. Note that it can only provide ACD, that is atomicity, consistency and durability, not isolation. So shadow copy is simply like this. Suppose you have your database in a file and you have to perform your transaction. Okay. Now before performing your transaction, make a copy of the database, that is copy the entire file into another file, okay, and make your changes on the copy of the database. Okay. Now if your changes succeed, that is it does not violate any integrity constraint, and it is consistent, and it is safe to commit and so on, then you simply delete the original database, and then you keep the new updated copy of the database. In case you have to abort your transaction, then you just delete the new copy that you have created and let the original database be in its place. So as simple as that. That is you make the entire database into a shadow, that is copy the entire database into another file and make changes on it, and if it is safe to commit the changes, then delete the original file, or if it is unsafe, then delete the new file and let the original file be as it is. Of course it is easy to see why it is impractical and inefficient, but of course does it satisfy the acid properties of a database? Let us look at atomicity. If I see that I cannot do all operations in a transaction such that atomicity needs to be met, then I just delete the new transaction, that is I just delete the new file, that is it is all or nothing, that is only when all operations are committed, all operations are performed in the new file will I delete the old file. So therefore it is all or nothing, no operations have been performed. Consistency, if any integrity constraint is violated in the new database, just delete it, so that assuming that the old database is consistent, we are still left in a consistent state. Okay. And isolation obviously is not supported, because whenever two or more transactions are copying or making different shadow copies, we cannot support isolation here. And durability, at any point in time, that is once a transaction commits, it just ensures that either the old file or the new file remains, that is once a transaction terminates, that is either commits or aborts. If it commits, then the new file remains, and if it aborts, then the old file remains. So it is durable, that is whatever changes were made are persistent in the database. Let us have a look at the concept of serializability, which is again very important when it comes to recovering from failed transactions. Like we mentioned before, in the previous shadow copy example, isolation was not supported, and in order to support isolation, we should ensure the notion of serializability in our transaction processing environment. The serializability simply says that if a set of activities from 2 or more concurrent transactions are taking place, they should be scheduled in such a fashion as though the transactions were executed in some serial order. So have a look at the slide here. It shows 2 different transactions, T1 and T2, and transaction T1 is a wire transfer, that is taking 50 rupees from A's account and putting it into B's account. Transaction T2 is also a wire transfer, that is taking 10% of whatever amount is there in A's account and crediting it into the B's account. Now suppose I were to perform all activities of T1 and then start with all activities of T2, obviously it is a serialized schedule. Such a schedule is called a serial schedule, that is performing all activities of one of the transactions before starting the first activity of the second transaction. So this is equivalent to performing T1 followed by T2. On the other hand, if I perform all activities of T2 and then start with the first activity of T1 and then perform all activities of T1, this is also a serial schedule, this is also a correct schedule, and this is equivalent to T2 followed by T1. However, serial schedules does not necessarily mean that all activities pertaining to a given transaction are completed before the first activity of the next transaction is even taken up. For example, this slide shows how activities from T1 and T2 are interleaved. The colored activities here belong to T2, that is read A, T equal to A times 0.1, A equal to A minus T, write A, and then the transaction T2 has not yet completed, but transaction T1 has already begun, read A equal to A minus 50, write A, and so on, okay, and then transaction T2 continues here and transaction T1 also continues here. However, if you notice, even this schedule is a serialized schedule or is a serial schedule. This schedule is equivalent to performing T2 followed by T1. Why is this so? Have a look here, have a look at how the activities of T2 and T1 are interleaved. All activities performing or regarding updation of data element A is completed of the transaction T2 or from the transaction T2 before the first operation involving data element A is even performed from transaction T1. The same thing with respect to B, and we can actually see that we can rewrite it, that is we can take these elements of B back here and put this back here without changing the semantics, that is without changing the overall semantics of the serialized schedule. That is, once this schedule finishes, it is equivalent to as though T2 was executed first followed by T1, that is as though all activities of T2 finished before the first activity of T1 ever started. This brings us to some definitions of how we can enforce serializability over a set of database activities. We define the term conflict serializability by first defining the term called conflicts between database activities. Then we say that a particular schedule is conflict serializable if there are no conflicts with respect to or when it is being transformed to a serialized schedule, that is a schedule in which all transactions or all activities of one transaction are performed before all activities of the second transaction. Now consider two activities I and J belonging to two different transactions T1 and T2. Now I and J can be swapped in their execution order if they refer to different data elements, because it does not matter, one is referring to element A and the other is referring to element B, and it does not matter, we can perform them in any order. And I and J can be swapped in their execution order even if they refer to the same data element, however all that they are doing is reading the contents of the data element. If both are just reading the same data element, does not matter who is reading first and who is reading second, as long as there is nothing else in between them. That is they are said to conflict, that is I and j cannot be swapped in the execution order if at least one of them is a write operation. That is, if at least if I is trying to write and j is trying to read, we cannot have and I should be performed before j, we cannot have j read the database before I writes it, and so on. And the same thing is true when both are write operations. Given a schedule S, a schedule is something like what we saw in the slide here, that is this is a schedule. Now suppose we are given a schedule like this, that is the activities of T2 are performed like this, and then activities of T1 are performed, and then activities of T2 continue, and so on. Now given a schedule, if we in order to determine whether it is safe or not, or whether it is serializable or not, we can identify this if we can swap, or if we can make one or more swappings of activities, database the schedule activities, and bring them to a serialized schedule, that is where all activities of one transaction are performed before all activities of the second transaction without encountering any conflicts as the way we defined in the previous slide, then this kind of a schedule is said to be a conflict equivalent schedule. Okay, and it is also said to be a conflict serializable schedule, that is it can be serialized, or it is equivalent to a serialized schedule where the equivalence criteria is conflict equivalence, that is conflict serializability. There is an alternate a weaker notion of serializability called view serializability. Conflict serializability is quite strong, and in many cases we do not need the stringent properties of conflict serializability. The view serializability simply says the following: suppose for each data item q, suppose there are a set of transactions that are happening in the in a DBMS system. Now for each data element q, suppose it was transaction Ti which reads the initial value of q in a serialized schedule, that is in a serialized schedule S, then in any other schedule which is view serializable, it should also be the case that the same transaction is the first transaction to be reading this data element S or this data element Q. And similarly for in the given schedule, for each data item Q, if Tj precedes or Tj writes to Q before Ti, that is before Ti reads, then the same dependency should be maintained in any other schedule, that is anybody writing to a data element before somebody else is reading it, this kind of dependency should be maintained in whatever if the schedule has to be view serializable. And similarly the last operation, that is whoever performs the final write in a serializable schedule, should be the same transaction who performs the final write in whichever schedule that is view serializable. Let us take an example. There are three transactions shown in this figure. The first transaction T1 reads data element Q and writes it back to disk after performing some operations, which is not really relevant here. It is only the reads and writes which we are concerned about. And T2 just writes something into Q, and T3 also just writes something into Q. Now the following set of the following schedule is a view equivalent schedule or a view serializable schedule. Note that it is not a pure serialized schedule, that is activities of T1 and T2 are being interleaved here. All activities of T1 are not completed before activities of T2 are performed. However, if you see who is reading the first, who is the first transaction to to read data element q. Suppose we take a serialized schedule, that is T1 followed by T2 followed by T3. If in that serialized schedule the first transaction to be reading data element q is T1, that is the same thing in this schedule as well. Okay. Now is there any read before write dependencies? There are. For example, T1 is reading before T2 is writing, okay, or rather and T1 is reading before T3 is writing. Is that dependency maintained here, that is write before reads or read before writes, either of those dependencies, they are maintained here, okay. And who is the last transaction writing to Q? It is T3. That is the same thing here, that is T3 is the last transaction that is writing to Q. Therefore this is a view equivalent schedule, that is it corresponds to T1 happening before T2 happening before T3, because the first data element to read was T1, read Q was T1, and the last element to write into Q was T3. So when T3 is finished, then there is no difference between saying it was performed as T1, T2, T3, or it was performed in this fashion here. However, note that this schedule is not conflict serializable. If we try to swap updates here, that is if we try to swap activities here in order to get to a serialized schedule, then we encounter a conflict. That is take a look at the second and third activities here. Now in order to bring it to a serialized schedule, we have to swap the second activity with the third activity, so that T1 comes here and T2 comes here. However, both of them are writes, and we saw that when both of them are write operations on the same data element and belong to two different transactions, then you cannot swap them, they are in conflict. Therefore this schedule is not conflict serializable, however it is view serializable, that is as far as the database view is concerned, it remains the same whenever we look before T1 or after T3, it has been the same. So every conflict serializable schedule is also view serializable. However, the converse is not true, which was the example we saw in the previous slide. Usually this thing happens, that is usually we find view serializable schedules that are not conflict serializable whenever there are what are called as blind writes. A blind write is something that we saw in the previous slide here, that is transactions T2 and T3 as shown in this slide contains no read operation, they just write into the database without any read operation. So such it is the hallmark of blind writes which bring in schedules that are view serializable but not conflict serializable. Let us look at the last concept of what are called as recoverable schedules, and in order to understand what kinds of what are the requirements for database recovery. Now consider the following set of transactions as shown in the slide here. There are two transactions here, T8 and T9. T8 reads a data element A, does some modifications and writes it, and then goes about reading some other data element and so on, okay. Now after it writes it here, transaction T9 reads the data element A and possibly let us say displays it, and it does not perform any writes, okay. So as you can see, this is a conflict equivalent schedule, that is I can swap read A with read B, which will give me a serialized schedule, that is TA followed by T9, and by swapping read B and read A, it is still conflict equivalent. So therefore performing read A, write A, read A of T9 and read B of T8 is conflict equivalent. However, suppose let us say T9, that is read A and display, okay, that is display the latest value of this stock price or whatever, okay. So suppose T9 commits and it displays the value of A, but T8 has not committed, that is T8 has not completed still, and it sees that it cannot commit because there is some problem somewhere, and it has to roll back. Now if it rolls back, then T9 also has to be rolled back, because it has read a value of A after it has been written by T8, okay. However, we cannot roll back T9 because it is already committed, and committed is note the durability condition here, that is we have already made some commitment in some sense, that is we have displayed the new value of the stock or whatever. Okay. So in such a situation it is impossible to recover from the failure of T8, because we cannot because the rolling back of T8 will also require rolling back of T9, which is impossible. So this is an example of a non-recoverable schedule. So serializability or config serializability alone is not enough. We need to also look at recoverability of a particular schedule of transaction events if we are to be able to recover from a database crash. So database systems require recoverable schedules. And finally let us have a look at the problem of cascading rollbacks, which is also quite important when it comes to recovery. Even if a schedule is recoverable, to recover from a failure of a transaction, there is sometimes a need to roll back several transactions. The previous example was also an example of a cascading rollback, that is suppose transaction T9 were not committed and transaction T8 rolled back, then transaction T9 also has to roll back. So, so in order to make it recoverable, we have to defer the commit of T9 until after T8 has been committed. So that will make it recoverable. However, it still contains the problem of cascading rollbacks. Okay. So this example also shows a cascading rollback situation where there are 3 transactions T, T1 and T2, and T has read a value of A and written it, and whatever value that is written by T is being read by T1 and T2. Now T1 and T2 cannot commit, that is cannot, let us say, display their display the new value of A until T has committed, otherwise it will become non-recoverable. Okay. Now even if they do not commit and suppose T has to roll back, it will cause a cascading effect in T1 and T2, that is in fact T2 is dependent on T1 and T1 is dependent on T. So a rollback of T will cause a rollback of T1, which in turn will cause a rollback of T2. Okay. So such cascading rollbacks will have to will lead to an undoing of a large amount of work from several different transactions in case of any database crash or system failure. So cascading rollback is an undesirable thing to happen and leads to a undoing of a lot of work. So when we are looking at schedules of operations that are performed by OLTP environments, they have to be not only serializable, they have to be recoverable and cascadeless, that is as far as possible we should try to avoid cascading rollbacks from occurring. So that brings us to the end of this introductory session on database recovery, where we have set the ground for all the issues that make up or that are to be that are concerned or that we have to concern ourselves with whenever we are dealing with database recovery. For example, we saw the notion of a transaction, that is when we are recovering from a database crash, we have to ensure that we do not leave any transactions in a half or partially committed state. It should either be fully committed or no operation should have performed, that is all or nothing. Atomicity of transactions have to be maintained whenever we are recovering from a database crash or a system crash, and in order for that to happen, we have to have recoverable schedules, and it is not sufficient for schedules to be serializable, and also whether it is conflict or view serializability, it is not sufficient for schedules to be just serializable. There should also be recoverable schedules, and as far as possible there should be cascadeless schedule, that is a crash or a rollback of one transaction should not automatically mean that several other transactions or several other work that has been partially completed has to be rolled back. it's not even partially completed, even though they are completed and just waiting for commits, which is what we saw in the previous operations in the previous slide. That is, even though transactions T1 and T2 have completed, they have read and written the value of A, they are just waiting for the original transaction to commit, and because of some problem the original transaction may crash, and because of that even all the operations that have been completed have to be rolled back without any reason, that is without any local reason by themselves. So this brings us to the end of this session.